CLI a cross-platform IDE for C and C++. Download now.
Hello, everyone, and welcome to cpponline. I'm Sarthak, and I'll be talking about type erasure in C++ standard library today. I'll start off with std function. We're going to build our own std function from scratch. And as we build the standard library container, we'll explore what type erasure is and how std function leverages that. It's a fundamental part of how std function is implemented. I'll start about highlighting what the std function's definition, the standard definition is, how it can be achieved, outlining requirements, then building the std function wrapper, a basic one, and then highlighting the costs associated with the std function. Further, we'll explore how std shared pointer uses a very similar technique of type erasure as std function, and how that technique is also fundamental to how std shared pointer is implemented. Before I dive into all these topics, a little about me. I'm Sarthak Sehgal. I'm a C++ software engineer based in Chicago. I work at a high-frequency options market making firm. As you can guess, I'm interested in finance, low-level programming, and C++ under the hood. In my free time, I write blog articles on finance and technology. You can check out my blog or just drop me a message on LinkedIn. So let's dive right into std function. So what does the standard define as the signature of a std function? As per CPP reference, std function is a class template, which is a general purpose polymorphic function wrapper. The interesting part here is the general purpose polymorphic phrase. Let's explore what all we can assign to a std function, and we'll unravel what exactly is meant by general purpose and polymorphic. So in this example, I've got this free function print num, which takes an argument, an integer I, and just prints out the integer. I can assign std. I've created a std function with a return type of void and taking a parameter of type integer. I'm calling that fdisplay. So it seems like we can assign free functions to a std function as long as the signature matches. What else can we assign to a std function? In this slide, I've got a lambda, which is very similar to the previous free function, except that now it's a lambda. But the signature is the same, essentially, that it takes an integer and the return type is void. And I can assign a lambda expression to the std function of same type. If you notice in this slide and the previous slide, the type of std function hasn't changed. Only the object being assigned to it has changed. In this slide, I've got a functor, which is a function object called print num, a struct called print num, which implements the function call operator. Again, same signature of the function call operator, takes an integer, returns void, and this can be assigned to a std function of same type as well. This is interesting. In the last three slides, the type of object being assigned to the std function changed, but on the left-hand side, the type of the std function was the same. So it seems like in C++, although it's like a strongly typed language, even with the same type on the left-hand side, we were able to assign three different concrete types, objects of three different concrete types to the std function. This is where the general purpose and polymorphic part of the definition comes in. It is polymorphic in the sense that you can assign different types as long as the signature matches. So this raises a big question. How are we able to assign completely unrelated types, for example, a free function, lambda expression, a functor, to a common type std function, returning a void and taking int as a parameter? So let's start off by building such a container, and let's start off by highlighting what the requirements of such a container would look like. So as we've discussed, the requirements, the first requirement is that the container should be able to hold different types, sharing a common interface. That is, it should be generic. The second requirement is that it should retain the type information of the assigned object. That is, it should be type safe. I haven't touched a lot into the type safety yet, but just bear with me, and we'll come into type safety when we look at shared pointer. It seems like an age-old concept called interfaces in C++ satisfy both the requirements. In this slide, I've got an interface called iFunction, which has a function called operator, takes an integer, returns a Boolean in this case, a bit different to the previous slides. This is a pure virtual method, so which makes the iFunction an interface. Then I've got two different implementations of that interface: is even functor and is odd functor. They implement the function call operator, and in case of is even functor, it returns true if the passed integer is even. In case of the is odd functor, it returns true if the passed integer is odd. And you can see that assume I have a filter range function which takes an input vector and then needs to filter given a certain functor, given a certain function, which just takes in the elements of the vectors, and returns true or false. So you can get a filtered range out of that vector. I can simply pass a const reference to the interface, and now this I can see once the filter range function accepts a const reference to the interface, I can either pass the object of type is even functor or is odd functor. So this seems to be satisfying both our requirements. It is generic and type safe. Interfaces are type safe as long as the destructor is virtual, so the destruction order is correct. But what's the shortcoming of this? The shortcoming is that by using an interface, the code introduces a requirement that any function that needs to be used by the filter range method must implement the iFunction interface. Imagine that you're using an external library which defines this filter range method, but you want to use your own filtration criteria. There's no way that you can implement, you're bound to implement the interface that is defined in an external library in order to use your own filtration criteria for the filter range method. So no external library function having an operator implementing the same interface, that is taking in an integer and returning a Boolean, can be used in filter range, despite satisfying the requirements we need. Like vice versa, you can think that imagine you need to use a filtration method from an external library. So there's free function, or there's this functor in an external library that you want to use as a filtration method. You can't pass that into this filter range method because that method, that function, or that functor does not satisfy the iFunction interface. So although interfaces satisfy our requirements, we need to come up with something better. But maybe in this case, our requirements were not completely correct. So let's take a step back and fix our requirements. When we previously defined the requirements, it said a whole different types sharing a common interface. But it's not exactly true, because the types need to be completely unrelated or related. Like they can be either. But it's not necessary that they need to be different, but more so important that the stood function needs to be able to pull completely unrelated types. That is, they're not bound by an interface hierarchy or any other sort of thing. As long as it satisfies a specific signature stood function, we should be able to assign them to a stood function. So let's start off by building a container that satisfies these requirements. At the end, the result should look something like this. We've got this magic function container, and three objects of the same type, magic function container, should be able to be assigned. We should be able to assign different objects of types like a free function, lambda, and a functor to this magic function container. So let's start with the first step. We've defined that the types that are being passed to this magic function container are completely unrelated. So you can infer that the magic function container should be constructible by different completely unrelated types. So let's start off with the step one, which is making a container which is constructible from completely unrelated types. In this slide, you can see that there's this struct magic function container. The important thing to note is that its constructor now is a templated constructor. So you can pass any type to the constructor, and it's simply gonna forward that object into this mval. And we'll come to what the type of mval is. And you can see that this function container also implements a function call operator, which returns the type void, takes an integer. And when this function call operator is called, it simply calls mval with that integer. So the interesting, this as long as we assume that we have defined the type of mval and it works and it's the correct type, the thing to note is that this function, this code is going to compile as long as mval can be called with an integer I. And that is what constrains this. And in the coming slides, I'll use C++ for any concepts to further constrain the constructor so that it does not simply accept any type func, and instead it's able to constrain that to types which only are callable by an integer. But the main challenge here remains to define the type of mval. We've seen that, okay, we've got a container that can be constructed using any type, completely unrelated types. That's the first step. But now, how do we store these completely unrelated types? Can we store mval as a base class type pointing to a derived class that implements the interface? I know it's a bit tricky when I say this, but let's have a look. Let's have a look at how we can store mval. So in this slide, I've defined a concept struct and a derived model, whose base class is this concept. The concept is a interface, as it contains a pure virtual method. The function call operator takes an integer, returns a void, and it has a virtual destructor just to ensure that destruction is correct. And then the interesting thing is this model is a templated structure. So it inherits from a structure which is not templated itself, but the model structure is templated on a type T. The model structure model of type T can be constructed from a value of type T, and it implements the function call operator that's defined in the concept and simply calls the value that was passed to it. You can see that in the model, in the constructor, it's copying the value and storing it into mval. So it implicitly requires the value to be copy constructible. And that's why I've got this asterisk at the bottom. I'm saying that any type T implementing the function call operator can be stored in model T, and model T inherits from concept. And there's a little asterisk there because it's not any type T. It requires the type to be copy constructible. Now, why are we even looking at all of this? So if you notice that with this concept and model hierarchy, what we've achieved is that a model and any type model T, as long as T is copy constructible and implements this function call operator, takes an integer and returns void, any type model T can be assigned to a pointer of type concept, because the model, all the types model T, inherit from concept. That's the beauty of this design. So let's have a look on how we're going to wire this into the magic function container, and you'll realize what's going on. Now, on the right side in my magic function container, I've still got the templated constructor. I've still got the function call operator. But if you notice now, I've got a type. I read in mval to mfunc, and now I've got a type for that. The mfunc is a concept pointer, which is by default null pointer. And in the templated constructor, now what I'm doing is that each time I get any type func, I'm creating a model of type func and passing that the object into this new type. So essentially, the concept pointer is always pointing to a model of type func, like model func, like model with a template type parameter func. That's what it's pointing to. So essentially, with this, what's going to happen is that although like you're able to store mfunc, which is not templated itself, like the magic function container is not templated itself, but its constructor is templated, and now mfunc is able to store different unrelated types. This is what stored function achieves. So you can pass the type name func can be any type as long as it satisfies the function call operator. This is the beauty of this design. Now we can do some templated magic, some concepts magic to constrain the type func, and then like some template magic to make this more generic. So I usually break for questions, but if you have any questions, feel free to mention them in the comments and I can address them. So drum roll for some template magic and some concepts magic, and let's look at a generic stored function container. So you can see this in this slide. I've got a function, a free function class, which is not defined, but a function class template specialization, which takes a return type R and periodic templates args. You can see that in the constructor, now I've got a requires clause. It requires that the type being passed is callable using the args and returns the same type as R. So just constraining the arguments. And then I'm doing the same thing. I'm creating a model of type, like I'm wrapping the function being passed into my own model of type T. And now I've got some return type and the arguments. It's essentially the same concept. And then the function call operator, you can see now returns a type R and takes in the arguments args. And I've got a little note here that this is not standard compliant. That's because for ease of implementation on line 23, I'm using a unique pointer. So this function is not copy constructible. It's only move constructible. So essentially, if you summarize the last few slides and look at what we did, we took various concrete types and wrapped them into a single generic interface, which is this function. And that is exactly what type erasure is. And how it is achieved is using this concept model hierarchy, wherein you're taking different concrete types, wrapping them into a model, into your own model type. And this model type you can store with a pointer of type concept. And this is how type erasure is achieved in a lot of standard stored function implementations. So let's take a look at what type erasure exactly is. Type erasure essentially enables you to use various concrete unrelated types through a single generic interface. There's some costs associated with the implementation of stored function as well. If you've been paying attention, we use virtual methods. So virtual function call introduce some runtime costs. We use heap allocation. For example, in this case, I had a unique pointer. In the constructor, I'm wrapping the function we passed into the unique pointer. So this is going to have some heap allocations. So let's have a look at what the cost of stored function is. Number one, there's heap allocations on construction. And number two, this virtual function calls. And I've got a little asterisk here again as well. That's because some standard implementations might do optimizations. One of the well-known optimization is small buffer optimization, wherein if your function signature is small enough, that is the size of the function is small enough, then there's not going to be any heap allocation. Although I think most of the implementation do have virtual function calls. And I'll link to, although I won't be talking about the small buffer optimization in this presentation, I'll link to an interesting article at the end of the slides. So Um, I've, I've touched quite a bit on first requirement, that is the type erasure, like this type erase container should have the ability to hold unrelated types sharing a common interface. But I haven't talked a lot about the second requirement, which I listed, that is type safety. That is, it should be able to retain the type information of the assigned object. Let's have a look into that. And I'm now gonna segue from std function to std shared pointer to have a look at why exactly type safety is important in type erasure. And we'll uncover that even std shared pointer implements a very similar technique to std function to type erase the deleter. Consider this example. I've got a pointer of type void star. The foo, I'm calling the variable foo_ptr, foo pointer, and I'm assigning this a class of type noisy foo. All noisy foo does is that on construction it makes some noise, that is it prints to the console constructed noisy foo. On destruction, it prints that it has destructed the class, destructed the object. And what I'm doing is that I'm creating noisy foo, and then I'm deleting it. Would this code compile? That is my question. What will be the output of this code? On GCC, it's going to say that deleting void pointer is undefined. On Clang 19, it's going to say that it cannot delete expression with pointer to void type void star. And this is because deleting a void pointer is undefined behavior as per standard. Let's have a look at another example. So say instead of a raw void pointer, I have a unique pointer now. I'm doing the same thing. I have a unique pointer of type void, and I'm assigning an object of type new noisy foo to this unique pointer. What do you think will be the output of this? It's the same thing. Although the error differs a bit, but the concept remains the same. As for standard, deleting a pointer of type void star is not allowed. As I listed here, it's undefined behavior. So it is allowed, but it is undefined behavior. But most of as you can see, GCC and Clang won't allow this code to be compiled. So we've seen that raw pointer does not work. A unique pointer does not work. What about a shared pointer? Again, doing the same thing. Now we have a shared pointer of type void, assigning an object of type noisy foo to that. What do you think will be the output? Interestingly, in this case, now it compiles and it prints the correct output, constructed noisy foo and destructed noisy foo. Now, how does this happen? Is a shared pointer not storing a pointer of void star, whereas a unique pointer is, and a raw pointer is clearly a pointer of void star? How is the shared pointer even able to delete the correct object when it's storing a pointer of void star? That's an interesting thing. So, imagine you have a pointer of type void star, and you've lost the type information. That is, once you've casted something to void star, you don't know what the original type was. How is shared pointer able to still store the information of the original type, that is noisy foo, in order to be able to destruct that correctly? And this is what I mean by type safety in type erasure. So even though shared pointer somehow seems to be, because this is a shared pointer of type void, the original type noisy foo is getting erased, but shared pointer stores the type information in order to be able to destruct the type correctly. So the type safety essentially comes in this case, for the destruction order of the type being passed. So as we saw, a shared pointer of type T stores both template type information and the object type information. So although in the previous slide, the shared pointer was the template type parameter for the shared pointer was void, but magically it's storing the object type information as well in order to destruct that correctly. And what it does is that it uses type erasure to call the correct destructor, and among other things, other applications of type erasure and shared pointer, as we'll uncover soon. Whereas unique pointer only stores the template type information. And you can see this, you can get a bit of a hint for this in the signature, like in the signature for the shared pointer and unique pointer. You can see in unique pointer, it takes the template type parameter t and also deleter. It defaults the deleter to default delete, which is simply called the delete operator. And this is why when we were passing a type void, it was defaulting the deleter to default delete of type void, which is not which is undefined behavior. But in the case of shared pointer, it does not even take a deleter as the template type parameter. It's what it does is that it simply assumes that the default deleter to be the deleter for the object type being passed instead of the template type t being passed. That is the important distinction between a unique pointer and a shared pointer. Shared pointer, the deleter is based on the object being passed during construction, whereas for the unique pointer, if you don't specify a deleter, the default deleter is based on the type being passed when you declare the unique pointer. So let's start off with a shared pointer implementation. Let's borrow the concepts that we learned previously from stored function implementation and try to come up with an implementation where we're able to store both the template type being passed. That's simple to store. That's a template type parameter. In shared pointer, we already know what that type is going to be, the type t. So we have access to that type, but also store the object type being passed. And as I say this, you can start to think that in case of stored function, it had the first step was to create a constructor which can be constructed using any type, as long as the type specifies the type meets the criteria of a specific signature function called signature. Similarly, in a shared pointer, we should be able to construct a shared pointer with any object, as long as the type of the object is convertible to this type t, or to be completely correct, the pointer of the type should be able to be convertible to pointer of type t. But let's have a look at the implementation. In this slide, I've just got another interesting example. I've got a shared pointer of void type ptr1 assigned in an object of type noisy foo, ptr2 assigned it to a different object noisy bar, which is a similar class, just outputs on construction and destruction. And an interesting thing to notice that all of these are completely unrelated classes, the noisy foo and noisy bar. We can assign the pointer to each other, like pointer one can be assigned pointer two, because the type of the shared pointer is the same. And this is achievable because shared pointer does some magic about the user's type erasure and does some magic in order to ensure that when I assign pointer two to pointer one, pointer two is destructed correctly. So let's have a look at what it does under the hood. This is a very simple shared pointer implementation. This is a class shared pointer. It has a template type parameter type t. It can be constructed only with that template type parameter type t. And on deletion, it simply deletes the pointer. If you're not aware, shared pointer stores the reference count. When we make a copy of a shared pointer, it simply increments the reference count. And a shared pointer, the object being stored is truly deleted only when the ref count goes to 0. That is, there's no object pointing to this. There's no shared pointer pointing to the object. Do you think this code compiles when I create a shared pointer with type base and pass it a type, an object of type a derived class, which is derived from the base class? Not really, right? Because the shared pointer expects that the type, the object being passed in construction is the same type as the template type parameter. And as I discussed previously, what we need to do is to have something similar to std function that is a templated constructor. So shared pointer needs to be aware of the actual type being passed during construction in order to delete it correctly. And we'll see how we achieve that. So a shared pointer with the template type parameter T1 can store objects of any type T2 as long as the pointer to type T2 is convertible to the pointer of type T1. And how it achieves is that it type erases this type T2. And on destruction, shared pointer will call the correct destructor, that is the destructor corresponding to this type T2 instead of type T1. Let's have a quick overview of a shared pointer class. In the previous basic example, I had the reference counter. In this example, I had a pointer of type T, and the reference counter is in the same shared pointer class. But it makes it easier to have a different structure for the reference counting. So let's have a look at what the usual implementations look like. In a shared pointer of type T, it stores a pointer to T, the object, and it also stores a pointer to control block. This control block is a different class. It stores reference count, week count, and some other data. For the sake of this presentation, all we are concerned about is the pointer to this object, and in the control block, the reference counting, and if you notice, the custom deleter. The custom deleter is the one which is going to be responsible to delete the correct object. But that is, instead of deleting the object to type of type T, it's going to delete the object which was passed to it during construction. So the first step, as in the example of std function, is to have a templated constructor. I think you're probably quite used to this by now. I've just simply changed the constructor to be a templated constructor. So now I can pass in any object to this. Later, I'll constrain this to ensure that this constructor only accepts types Y, such that the pointer to Y is convertible to pointer to T. You can see in this slide, I've added the concepts to ensure that the pointer to Y is convertible to pointer to T. So now we've got a templated constructor. I've added another constructor in this slide, which is, you can see the second constructor. It takes a pointer of type Y, Y star, and then a deleter. And this is like any deleter. The default deleter in the first constructor is to default delete, same as unique pointer, but you can pass, it allows clients to pass a custom deleter as well. Now, how do we, the pointer to Y is convertible to pointer to T. So in this case, you can imagine that the pointer itself is simply stored as, is simply stored in the class as T star. So I've got T star and PTR at the bottom. So simply I can store the PTR in the member PTR, as I've done in the second constructor. But the interesting thing is, how do we store the deleter? And we've lost the information of the original type Y at this point. As soon as I converted the pointer, as soon as I assigned the member pointer, which is T star, a pointer of Y star, I've lost the information of the type Y. So that's the interesting part. How do we store the deleter and the true type of the object that is Y? And we're going to use a very similar technique as we saw in std function. In this slide, I've got a control block, similar to what I explained previously. So you can see that this is very similar to the model, the concept model interface hierarchy that we saw in std function. The control block base is a concept which shows the reference count and has a virtual deleter. The control block inherits from the control block base, and it is templated. So the concept itself is not templated, but the model, which is the control block, is templated. And in this case, it's templated on two types, the object type and the deleter. And what it stores is a pointer of the real object type. Now, this is not going to be the type parameter of the shared pointer, which was p1, but it's going to be the type of the object being passed to the shared pointer during construction. So this is going to be the real type of the object. And then it stores the deleter. And you can see that it can be constructed using the pointer and deleter. And on destruction, it calls the deleter with this pointer. That's the interesting part here. So whenever this control block is deleted or is destructed, it's going to call the deleter with the correct type. It's not going to call the deleter with the template type to shared pointer, but the actual object type. So you can see that this is very similar to the concept model hierarchy that we previously saw. And you can probably now imagine how we're going to use this in the shared pointer. The shared pointer stores now on the left a pointer of type t, and then a pointer to the control block base. On construction, in the second constructor, you can see that pointer to type y is assigned to the pointer of type t, and then I'm creating a new control block each time, which takes the actual type of the pointer y. So instead of when you store that as a pointer of type t, we lost the type information y, but now we are storing a control block which retains the type information. Although we've type erased it in the class shared pointer itself, but the control block implementation is storing the type to ensure that the correct deleter is called during destruction. So shared pointer with a type, this is the example of shared pointer with a type erased deleter. Notice that two shared pointer with same managed object type, but different deleter types can be assigned to each other. So as long as in a couple of slides ago, I had a shared pointer of type void, like template type parameter void, and it had an object of type noisy foo being assigned to it, and a shared pointer, again a shared pointer of template type parameter void, and it had an object of type noisy bar being assigned to it. And these are two completely unrelated objects, noisy foo, noisy bar, completely unrelated. But the shared pointer shares the same signature. As long as the shared pointer, in this case, shares the same signature, these pointer types can be assigned to each other, and the destruction is going to be correct. And you can see that with this implementation, it allows two completely unrelated objects being assigned to this shared pointer of type t. And I touched a bit before on why a shared pointer of type void is allowed, whereas a unique pointer of type void with a default deleter won't compile. And you can see here that what the shared pointer does is, in the first constructor, you can see that when you're not passing a deleter, it uses the default deleter of the object type. So it retains the information of the object type. That's the important thing. It does not use a default deleter of the type t, that is void in our case. It uses a default deleter of type y, which is the object type. And although this is not a complete implementation, you can implement copy constructors, move constructors. The copy constructor will only increment the reference count as long as pointer is not null. The move constructor is going to simply move the move the control block, assign the pointers to null, and I'll share the slides and link to the complete implementation of a shared pointer, which would be close to how the standard implementations were implemented. If you have any questions related to any of the slides, please feel free to mention them in the comments. If you have any suggestions, any comments, anything, please feel free to mention them in the comments. And there's pretty interesting readings on type erasure. I particularly like Andre's blog on type erasure, in which he covers different types of techniques, from void pointers to the techniques I discussed today, that is using the concept model hierarchy. And there's other techniques like a void star based type erasure, which is a modern void star. If you ever use std any in C++, std any is often known to be a modern void pointer because it is type safe, and it has a little bit of a different implementation. For the strip function, I touched on the cost associated with the strip function. And I mentioned that standard implementations do an optimization, which is known as small buffer optimization, or SBO, which is when your function signature is small enough, it's not going to do any keep allocation. This is an interesting thing as well, and I've linked that in the slides. Thank you so much for listening to my presentation today, and hope you enjoyed it. If you have any questions, comments, feel free to mention them. Cheers.